Thank you. So A11 x1 squared times x1 squared plus A12 x1 x2 plus A22 of x2 squared plus B1x B1x1 plus B2x2 plus C equals 0. And we separated the part with the quadratic part and the linear part and the constant. And so the step 1 says, write the equation in the matrix form of the quadratic.
So in matrix form,
Yes.
it's going to
So
be,
it would be so
so
it would
first
be,
of all, it's going to be we have, so it's going to be one row, one column.
mm-hmm.
It's going to be one row, one column. And this could be, oh, what do we write? This is a matrix. Is this x1 or, oh, this is just x2, right?
X2 to, yeah, X2 squared, yes.
Yeah, x2 squared. So it means this one should be x. This one should be x. And then we can have x2, x2.
So in my book, lectures book, the teacher wrote that the conic equation in the matrix form is the vector x transpose times A times vector x plus the vector B transpose times vector x plus C equals 0.
Plus the
B, yes.
Plus the
transpose.
vector B transpose?
Yes. B vector transpose times X vector transpose, no, just times X plus C equals 0.
So in this case, we could say x1, x2.
X2, yeah.
And then we could have A11, A12, A11, A12, A21, A22. Why don't we have, or maybe A21 is going to be 0? You think so? And then,
he wrote A11, A1, a half A12, then a half A12 again, then A22.
Yeah, so this is a half A12, a half A12. And then now if you multiply, this gives you the quadratic part.
Yes.
And this happens for any conic?
Yeah.
All right. Now, looking at this form of the conic, how do you know that it's going to be a parabola, a hyperbola, or what? We must have some few conditions because this is just a conic, right?
Yeah.
It could be a circle. It could be an ellipse. It could be a parabola. It could be a hyperbola, right?
Yes.
It could be, yeah, those four. So how would you tell if it's a circle, an ellipse, a parabola, or a hyperbola?
But after doing the quadratic, after doing the matrix form,
Mhm.
then there's like few more steps to at the end know if it's a circle, ellipse, or parabola, or hyperbole.
Okay.
There's 4 steps.
Yeah. So the first step, what is the first one?
So the first one was to write the equation in matrix form. So what we just did.
So we've already done the first one. Okay.
Yes.
The second one. So let me finish writing this. So that's the quadratic part. And then this other part, it's going to be plus B1, B2, X1, X2, and then plus a constant equals 0.
Yes.
Okay, so what happens in the next part?
Then he says, step 2, orthogonality. No, orthogonally diagonalize A.
Okay, so let's diagonalize A. So let's write the problem. So step 1 is to diagonalize A, right?
Yes.
And then step 2.
And make it orthogonal.
Yeah, so that is still step 1. So it's orthogonally diagonalize A. That's what it says.
Yes.
So you have to diagonalize A and you have to make it orthogonal.
Yes.
So this is going to become, so we had a diagonalization process where you use eigenvalues and eigenvectors, right?
Mm-hmm.
Okay, next step. I just want you to give me the list of steps and then we can use them to solve.
Mm-hmm. Next step is complete the squares.
Okay. So complete the squares.
And then translate the center.
Oh no, translate the center.
Yeah.
This sounds so new to me.
Translate the center.
So, okay.
But otherwise, how would you do it? How would you find with the equation? How would you know if it's a parabola or hyperbole?
I would have to reduce it to its usual form, like without using matrices. But I think, the problem we had, it's a problem that forces us to use matrices, because remember, I tried to do it last time using
Yes.
the usual formula, but it failed. Yeah. Okay.
But how do you orthogonally diagonalize A?
You can do that by finding its eigenvectors and eigenvalues.
Okay.
Yeah. I'm just looking into your book. See if I'll find that. Yeah, I think I can see it. Sylvester's law of inertia. Okay, can we go through this example?
I cannot see the page.
Okay, let me share my screen. Just a second. Okay. So these are the conditions I was talking about actually. Let me share my screen. So here's a theorem about quadratic forms. But now this theorem tells us to check conditions for hyperbola or ellipse. So when you have a quadratic form like this one, if you find a way of equating it to 1, then you should just check whether the discriminant is less than 0. If it is less than 0, then it's an ellipse. If it is greater than 0, it becomes a hyperbola. Okay. All right, I think we have to. So there is a diagonalization theorem, but this one we already did. So let Qx dAx be a quadratic form in those variables where x is that and A is symmetric matrix n by n. Let P be an orthogonal matrix such that is diagonal, and define new variables that by that. If Q is expressed in terms of these new variables, y1, y2, ym, the result is given as this, where lambda 1 up to lambda n are eigenvalues of A repeated according to their multiplicities. So let's go to the question. Can you see the question, or maybe you can just see the previous screen?
No, I can see the question.
Okay. So we could write this as xy like that. And then we have the matrix 1, -1, -1, 1, and then x, y, that way. And then next we are going to have 0. For the b, this is px plus by. So this is going to be square root of 2, 0,
0,
x1,
x1, x2.
yeah, okay, I could
So
just
x2,
use my x2
yeah,
is
x2
y.
would be y. Yes.
Yeah. And then we can diagonalize this matrix. So we need to find its eigenvectors. So the eigenvectors, we would do 1 minus lambda squared minus 1 equals 0.
Yeah.
And so 1 minus lambda squared equals 1. And so 1 minus lambda could be equal to 1, or 1 minus lambda could be equal to -1, meaning that lambda could be equal to 0, or lambda could be equal to 2. So we have lambda equals 0 and 2. So eigenvectors associated with that. So we can have, when lambda is 0, we get these eigenvectors. When lambda is 0, we are going to have the eigenvector 1, 1, right?
Yes.
And then when lambda is 2, we're going to get the eigenvector -1, -1, -1, -1. We're going to get the eigenvector 1, -1. And so we could write this as xy, xy, 1, 1. So this is 1, 1, 1, -1. And then we have 0, 2, 0, 0.
Yeah.
And then the inverse of this, 1, 1, 1, -1. First of all, the determinant is going to be -1 minus 1. Determinant is -2. So it's going to be 1 over -2. -1, -1, -1, -1, 1.
So it would be
-1, -1, 1. So let's see. 1 times 0, 1 times 0, that's 0.
They're going to be -2.
0, 0, 0, 2.
2.
0,
0, 0,
0, 0,
and 0, -2.
-2. 0, 2. Not making sense. Oh, yeah, it's making sense. 0, 2, 0, negative 2, 0, 0, 2, 0, negative 2. And remember, we have 1 over 2 down there. So this is 1, negative 1, 1, negative 1. It's not the original matrix.
I'm a bit confused how, but isn't minus your diagonalized the inverse matrix of the eigenvectors, but is it not a half?
Yeah, there is a half.
Yeah.
There is a half out there. Like we can put it here, right? So I was just trying to see if we have done our diagonalization correctly. Okay.
So the equation of diagonalization is D equals eigenvector times A times the inverse of eigenvectors.
Wait. This is positive too. I'm just trying to confirm whether this is right. So I'm multiplying these two matrices. Can you check? 0.
So 0, 0.
2, positive 2.
Then
0.
1, 2. Yeah, it is correct. Minus 2, yeah.
And then minus 1, minus 1, minus 1, 1. So 0
negative
minus
2.
Negative 2. It's not right.
So maybe the inverse is wrong.
Yeah, let's check
whether. Wait, is it not? Because so A equals 0, 0, 0, 2.
Yeah.
Correct. But we want the diagonalized of A. So wouldn't be
this is
the inverse?
No,
times
A is this one. So the diagonalized of A is this one. And it's the one we are checking whether it's working. Oh, just once.
Normally don't you diagonalize the eigenvectors?
We are trying to diagonalize A, and then we are using eigenvectors to do that. So I see what we did. I think this inverse should be up front.
Yes, that was what I was trying to say. That as we want the diagonalized of A, so it would be D equals P inverse times A.
The inverse should come up front. So let's now look at it. 0, 0, right? 0, negative 2. 0, 0, 0, 2. 0.
Is it not negative
0.
a half?
I have my 1/2 out there. I'll multiply it later.
But is it not a negative a half?
It's negative a half.
Yeah.
Why am I confused? It's negative. We have 1, 1, 1, negative 1. This is negative 1 minus 1 it's negative a half. Oh, okay. And if it's negative a half, then whatever we did was right. That was the small mistake. Can you confirm?
Wait, I'm a bit confused. Could we just restart all from the eigenvectors?
Okay. And so this is our matrix A. And this is what we are trying to diagonalize, right? Okay.
Mm-hmm.
So we want to write A as A equals P inverse D P. And P is going to be a matrix that is formed using eigenvectors of A. Right? And then D is a matrix whereby we are going to use the eigenvalues to get the diagonal entries. And then if we find the inverse of P, we get our first P inverse. So let's get the eigenvalues. Can you get the eigenvalues of A?
So the eigenvalues of A would be so 1 minus 1. So 1 minus lambda. So we should do step by step so we just understand
1 minus
everything.
lambda. Okay, I agree.
No, I was thinking about doing everything like so I'm sorry, I'm getting confused too. 1 minus lambda minus 1 minus 1 and 1 minus lambda. We just do it everything so it goes
Smoothly.
smooth. Yes.
And then we equate the determinant to 0.
Determinant, yes. So the determinant will be 1 minus lambda squared minus 2. No, sorry, 1 minus 1 equals 0.
Okay.
Therefore, 1 minus lambda squared equals 1. So lambda should equals 1 or no, lambda should equal 1 minus lambda should equal 1 or minus 1. Therefore, lambda should be 0 or 2.
And so the matrix D.
So the matrix D would equal wait, but we need.
We only need the eigenvalues to create the matrix D, the diagonal matrix D.
Yeah, so the matrix D equals 0, 0, and 0, 2. Yeah. And P would equal the eigenvectors.
Yeah.
So we need to find out the eigenvectors of lambda 0. So it would be 1 minus 0 minus 1 minus 1 and 1 times xy should equals to 0. So x minus y equals 0 and minus x, yes, so x equals y.
Yeah.
And so if x equals y doesn't mean how do I know the value? So it's just 1. If I say x equals 1, then it's 1, 1.
So 1, 1.
1, 1. So I do the same for eigenvalue 2, which would be 1, minus 1, minus 1, minus 1, and minus 1. xy. So it is minus x minus x minus y equals 0. So x equals y. My x equals minus 1. Therefore it is 1 and minus 1.
So we have D, we have P.
Yeah, and now we need to find the inverse of P. So the inverse of P would be, I just use my technique of the identity.
Okay.
The echelon form.
Just use it and get us P inverse. And then I'll use mine and see if we get the same answer. I didn't know we could use matrices to classify conics. I just discovered that today, thanks to you. And it's really working nicely.
So I got 1 over 2, 1 over 2, 1 over 2, and minus 1 over 2.
That's
so,
the same thing.
Yes, the same thing.
And so we could write our form as xy. And then we replace A with P inverse.
Yes.
1 over 2, 1 over 2, 1 over 2, negative 1 over 2. And then we have xy. No, not xy, but 0, 0, 0, 2. And then we have 1, 1, 1, negative 1. And then xy. And then plus square root 2,
0,
0,
xy.
xy,
xy plus 2, which is the constant, equals 0.
plus 2. like that. Okay. And so this is going to be a half x plus a half y, right?
Yes. A half x. Yes, a half x plus a half y.
Okay.
Then a half x minus a half y.
And then this is 0,
Mm-hmm.
0, 0, 2.
2. 1, 1, 1 minus 1.
Can we multiply this? X plus y.
So it would be x plus y
X
and
plus
x
y.
minus y. X plus y and x minus y. Plus square root of x 0.
Okay. So let me keep that. Let me just keep this. X, y
But here you did
is 2 equals 0. Uh-huh.
you did p inverse times a times p.
Yeah.
But is it not p times d times p inverse?
I think both ways work. Can we test it?
Yeah.
So if we multiply this, we get 0, 0, right?
Yes.
And then 0, 1,
And 1. Yes.
0, 0,
0
0
minus 1.
minus 1. And then 1, 1, 1 minus 1,
Yes.
0, 1,
And 1.
0
0
minus 1,
minus 1.
0
0
minus 1, 0,
0
1.
1.
So it's okay.
A diagonalized.
Yeah. It's equal to the same matrix A, but now it's diagonalized. Okay, can we factor out a half from the first thing?
Yes. So it would be
It's going to be a half x plus y comma x minus y, right?
yes.
It's going to be a half x plus y comma x minus y. And then if we multiply everything by 2, this is going to be,
Why would you multiply everything by 2?
to like eliminate the 1/2.
Oh, so okay. then it will be then 0, 0, 0, 4. Then
No,
2.
no, this is already multiplied. So the only thing that's going to change is this part, this part. You know, this has 4 parts, like the first part.
Yes. Yes, yes.
Yeah.
So 2 times square root of 2.
So it's going to be 2 root 2
And the 4.
and the 4. Okay. Now let's see what happens. What happens when we multiply them out? We get 0,
0.
0. We get 0, 0, 0, 0. So that's 0, right?
0
And then 0,
2x minus 2, 1.
2x minus y. And then what happens when you multiply this by x plus y over x minus y?
Then it's 0, 2x squared.
So this is x plus y, x minus y. So this becomes 2 x minus y squared, right?
Yes. So we basically just simplified x squared minus 2xy plus a plus y squared.
Yes. And it's taking us back to the original thing. Okay. Let's see what they've done in the solution. So we
But the problem of this,
mhm.
if I do 2 times x minus y squared, it doesn't equal x squared minus 2xy plus
No,
x
it
y
equals,
squared.
it's going to be, whatever we are going to get is going to be this guy multiplied by 2.
Yes.
Yeah, which is the same thing because we are going to divide by 2 and get back to the original format. Oh, okay. Can I try to do it without, okay, just a sec. So this is x squared. 2xy is the same as minus xy minus xy plus
Yes.
y squared plus square root of 2x plus 2 equals 0, right?
Yes.
So I could bring the x's together like x squared minus xy plus x root 2 and then I could have the y squared minus xy, and then I just have 2 in the end. So the only way to complete this square, x squared minus xy plus something that completes the square. Oh, we have this as well. So this is going to be x squared. So we factor out x. So this is going to be minus y minus square root of 2 x plus something that completes the box. Then we're going to have y squared minus xy plus some box plus 2 equals 0. And so this is going to be x squared. Whatever goes in the box is going to be the y minus 2 over 2. So this is going to be x squared minus y over square root of 2 over 2. No, this is simply x, like that. And then this is going to be plus y minus x over 2 squared plus 2 minus y minus the square root of 2 squared over 4 minus x squared over 4 equals 0. I feel like giving up on this problem today because I didn't get what I wanted. We have y minus square root of 2. It didn't simplify the way I thought it would.
Yeah, maybe because the teacher wants me to use his technique.
Yes, and it seems like there is only one technique. So let's try to understand his work then. So the characteristic polynomial is this. We already did this, right? And I remember we got eigenvalues 0 and 2.
Yes.
Find the eigenspace. We also got this. So we found this eigenspace. Did we get
we
this?
Didn't. Yes. Yes, that was when z equals any number. So you had 0, 0, 1.
Okay, and then we normalized it. We got another normal basis containing eigenvectors of A. Observe that the matrix of this conic is this. We also had this. So we see that eigenvalues are 0 and 2, and the other normal basis of eigenvectors is that the change of coordinates, x prime plus y prime over square root of 2, y equals x prime minus y prime over square root of 2, gives us this equation. Completing the square, we rewrite the equation. So is it okay if you send me pictures of what you did in class, right? Yeah, just send me pictures of what you did in class. I need to look into this matter.
Should I send it to you now?
Actually, you should do it now, because if you have a problem like mine, you may never do it. But
we could continue. We didn't finish the way he his type of
what?
Like we started doing the matrix form, then we started to diagonalize it.
Yeah.
But there's many steps after. So I think maybe if we continue.
The normalizing it.
Yes.
Okay.
So I'm gonna send you the text, the lecture of what I did.
You see, we did up to this, right? We did up to this point, right?
Yes.
You know, my question is, something I'm not understanding is this. Why is he changing the coordinates to this? what is the reasoning behind that? That is something that is not ringing a bell. That's my major problem. And that is this sentence. For example, completing the square. This is something I know how to do, right? Everything. But now the part where he changes the coordinates into this stuff, that's the only part that is giving me a headache. Oh, okay, let's see. Oh, I see why. You see the basis that we were working with for X and Y, it was the usual basis 1, 0, 0, 1, right?
Mm-hmm.
So I think it's just adding. For example, if you do 1 over root 2 plus 1 over root 2. So he just sets. I think this change of basis is depending on the new basis that we form. He's setting X equals 1 over square root of 2x, and then 1 over square root of 2 xy. X prime, y prime. Because if you do that, you're going to get x prime over square root of 2 plus y prime over square root of 2. And this is what he gets as x prime plus y prime over square root of 2. So I can see how he got the coordinates, but still the mathematics behind that, like the rules that he used, the reasons why he decided this way, it's something that we should look into.
Mm-hmm.
Yeah.
Yeah. I sent you the pictures, so if you want to take a look. So in the pictures, there's so we did with the teacher, we did in the same time an exercise and also the lecture. So it's like it's made step by step.
Yeah.
It might be a bit confusing, or maybe the picture are not in order too. So normally, if you see step 1 should be the first, then step 2, step 3, and there's 4 steps.
Okay. Okay. So I can see he's applying isometries and translations. Translating the center. Is it okay if we revisit? You know, Diagonalizing, that's easy. Okay, images. I downloaded the images and I cannot find them. Oh, okay, albums. Yeah, found them. So let's go through this one. Is it okay if we go through your class example?
Yeah, that's fine.
And try to,
Mm-hmm.
we are going to understand it, and then we are going to see why he is transforming and translating. So we have, is it 3x squared or is this 8? I see 3 x1 squared plus 2 x1 x2
Yes.
plus 3
Plus 3x2 squared
x2 squared
minus 1 equals
0.
0.
So check, change coordinates to y2 y. So he's changing coordinates. So we need to find the change coordinate.
No, I think
the equation.
no, I think the example you're talking about is an example of the page before. I think the one is the next page where the step 2, it says what type of conic is, then
Okay.
it says the equation of the conic. It is it's like in a square in the page where it says step 2, orthogonally diagonalization.
Okay, let me
Do
find that.
you see it?
Yeah, let me check that.
It's a bit messy, but there's some arrows going everywhere.
Yeah. I see step 3, complete the square.
Can you see it?
No, let me open it from my laptop and then I can share and then you can show me.
Okay.
It's my laptop is not opening the pictures for some reason.
Anyway, it's the one image 8933.
Okay, image 8.
8933 and 3. Oh no, yes, 8933. On the top it says running example.
Okay. Image 8933. Okay, I see it. So we have x1 squared minus 4x1 x2
Yes.
plus x2. Yeah, I see it.
So x1 squared minus x1, x2.
Is it minus x1 x2 or minus 4?
Oh, sorry, minus 4x1 times x2 plus x2 squared minus 2x1 plus 4x2 minus 1.
Minus 1 equals 0. So the first step, we write this as x1. So solution. So we write it using quadratic forms. So we're going to have x1, x2. 1 minus 2 minus 2, 1.
Yes.
x1, x2 plus
minus 2,
minus 2,
4, x1, x2,
x1, x2
minus 1.
minus 1 equals 0. So the first step, we orthogonally diagonalize A. Okay.
Yeah, so the first step was to make it as a matrix. And we did.
So that is something we can do. Next image, can you give me the code for the next image? So let's get the orthogonal. If we orthogonalize it, 1 minus 2 minus 2, 1, it's going to be equal to, so this is A, right? We need D, the diagonal matrix, and P for the eigenvalues, right?
Yes.
So let's get the eigen, but we have the eigenvectors in the question, right? I don't think we should waste our time looking for them.
Yes, at the end it says, so the eigenvalues of A is lambda 1 equals 3 and lambda 2 equals -1. And the eigenvectors of A is 1, -1, and 1, 1. It says
So-
at the end of the page.
So eigenvalues of A become
3 and -1.
okay. You're saying it says that at the end of the page?
Yes.
Okay, so we can say 3 and -1 for the diagonal entries. And then the P, the eigenvectors.
Eigenvector is 1, -1, and 1, 1.
1 minus 1 and 1, 1, like that?
Yes.
Okay. So I want to see what happens after that.
So after that, the page is step 3.
So which image?
Image. Oh, 8, 9, 3, 4, I think. Yes, 8, 9, 3, 4.
And so we are getting the orthogonal basis for the P, right? One over root 2, 1, 1, 1 over root 2,
Yes. I don't know.
1, 1. Oh, this is 1, -1. And then there is the change of coordinates. So there is this thing they're calling S equals the matrix, where we are changing from a base E to B.
Yeah.
With the identity on R2, it's going to equal 1 over square root of 2, 1, 1, -1, 1. So change the coordinates. So you just let X be equal to S, Y.
Do
So
you know
let
why
X be
they
equal to-
changed coordinates?
I think it's just a method. I don't really know why they're changing coordinates. So I see how you change the coordinates. You just replace X with the matrix S multiplied by Y1, Y2.
Yes.
And then you substitute and simplify. So you write the diagonal matrix directly. And you get something new. Can we revisit the problem? Because when it comes to completing the square, he's using the eigenvalues again. I think I
Wait,
should, yeah.
What does it mean by complete the squares?
So to complete the square, for example, if you are given a quadratic like x minus 8 squared, right? This
Yes.
is a complete square because it's a complete square already. So the equation x squared minus 16x plus 64, we're going to say it's a complete square because you're going to factor it into the same, it's going to have two identical factors. That's a complete square, okay?
Okay.
For example, if you look at the equation, x squared plus 6x plus 9, do you think it's a complete square?
Yes.
Because we could write it as x plus 3 squared, right?
Yes.
How about x squared plus 5x, okay, x squared plus 6x plus 5. Do you think it's a complete square?
No.
No, right?
Yeah, no.
It's not a complete square. Question is, can you complete it? Can you, because it's not a complete square, can you complete it? You see, you can complete it by doing x squared plus 6x plus some number that makes this equation a perfect square, but you have to subtract that same number because you don't want to change how your equation looks like, right?
Yes.
What if you do 9 minus 9? Realize 9 minus 9 is 0, so you haven't done anything. But realize x squared plus 6x plus 9 is already x plus 3 squared, right? And
Yes.
minus 9 plus 5 is minus 4, and so you have completed it. You have done the process of completing the square.
Okay.
Yeah. So that's how the completing the square method works. Yeah.
Okay.
Okay. Yeah. That question is stressing you up.
Stressing.
It's stressing us up. I was thinking we could like give it time. Personally, I think I need time to look at the examples you sent me and also
Yes.
to read a book, because for me to be able to explain it nicely, I really need to understand it.
Okay.
So
So next time we see each other, we could
yeah,
do this.
yeah, we can just save it for next time.
Okay.
Yeah, actually,
So
looking at conics as matrices is something I saw today. We usually look at them as we really don't. I've never used a quadratic form for the conic, but I knew it had a quadratic form, but I never used it before. We used other methods, and these methods are not working for that conic. Yeah.
And there is the similar thing for also quadrics.
There's a similar thing for that?
Yes, for quadrics too.
A quadratic is a conic, right?
A quadric.
Quadric?
So the conic and the quadric. The conic is two-dimensional, and the quadric is three-dimensional.
Oh, okay. A quadric is like a three-dimensional conic.
Yes.
Like a rugby ball. You know rugby?
Yes.
Okay. So an ellipse would be, the quadric form of the ellipse would be the rugby ball. Yeah. Okay.
So today, what could we do? We still have some time left.
Yeah, we do. We do have some time left.
We could start another paper, exam paper.
I'd like that.
So I'm going to send you another one.
Yeah. So for this exam paper, I think the only question that really stumped me was question 3B. All the others were good.
So let's try this one. I sent you the exam paper.
Okay.
I sent you also the solutions.
All right. Okay. Can we start with number 2 or number 1?
Let's start with number 1.
Okay. So we have Z and W. These are complex numbers.
Mhm.
So the modulus of Z plus the modulus of W is equal to the modulus of Z plus the modulus of W. So let's use an example to check whether this will always be right. Can you take a number Z equals
5.
it has to be complex, so it's going to have
Complex.
an imaginary part and a real
5i.
part. Yeah.
Yeah. Okay. 5 plus 3i.
Think of another number, just random, just be random.
7 minus 4i.
7 minus 4i. Now can you look for Z bar, the modulus of Z, the modulus of W?
What the modulus, is that the absolute value?
Yeah, but now for complex numbers, we have to, the process is a bit long, just a bit. For example, 5 plus 3i, this is the imaginary axis, and this is the real axis.
Yes.
So if this is a 5, and on the imaginary axis you have 3, and this is your number 5 plus 3i, right?
Yes.
So its modulus is going to be the distance between that number and the origin. Okay.
Okay.
And if you use Pythagoras theorem, in this case, we can use Pythagoras theorem to find that distance. Because you see, this is going to be a 90, 5, 3. And so this distance is going to be the square root of? The square root of 34, right? Okay.
Yes.
And so the modulus of your number Z is the square root of 34. Can you find the modulus of W using the same procedure?
So it would be 7 minus 4, 4i. So it's the square root of 7 squared plus 4 squared, which would be 49 plus 16. So it would be 65, square root of 65.
Square root of 65. Now, can you do z plus w? Just adding the two complex numbers.
Z plus W would be 12 minus 1i.
Now, can you find the modulus of 12 minus I?
So 12 minus square root of 12 by square root of 12 minus 1, so it would be square root of 11.
No. It's going to be the square root of 145.
Oh, yes.
Okay.
I forgot the
Yeah, now using these random numbers, do you think part one is true?
no, it's wrong.
So part one is wrong, right?
Yes.
Okay. Now, let's keep using the same numbers. Remember, we picked them randomly. They were so random.
Yes.
And I think we have this W is 7 minus 4i. So it's 7. And then minus 4i. W is down there. W is there. Now let's find the arguments. For example, let's find the argument of z, this angle, right?
Yes.
So what is this angle theta? If you use trigonometry, it's going to be arctan 3/5, right?
Yes.
And so if,
which is,
can you compute that?
yes, I have my calculator. 3, 5. It would be around 31 degrees.
Let's call it 31 degrees. Okay. And so the argument of that argument is 31 degrees.
Yes.
Now let's find the argument of this other angle. So you have to do, this is 7 and 4. So you have to do tan inverse 7/4. And then you have to do 360 minus that to get the argument.
But so the argument is what? Is it the
angle?
So it's 31 for Z.
For Z, the argument is 31.
But if you multiply two arguments, how does that work? So you just multiply 31 times, let's say 27.
Yes. For example, the argument of the second angle is 299.74. Let's call it 300. Okay.
How is it 300? From the x-axis.
Yeah,
So
from-
300 all the way around. Okay.
Yeah, all the way around. Now let's do z times w. Can you multiply z and w?
So 31 times 300.
No, z and w.
Oh, so it's 5 times 7, 35.
35.
Sorry, 35 times 5 times minus 4i is minus 20i
Minus 20i.
plus 21i
It's 21i.
minus 12i squared.
So also minus 12i squared, right?
Yeah,
But-
I squared is minus 1.
I squared is minus 1, so this becomes plus
Yeah,
12.
yeah.
So this is
Yes.
going to be 35 plus 12,
46, 47.
47. And then this is
and
plus I.
plus I. Yes.
And you can see that angle is going to be very small.
Yeah,
Do you think the second,
it's wrong.
it's wrong? Okay. Next, let us use the z plus 5i to check things out.
So 5 plus 3i times 5 minus 3i
Yeah,
is equal to, but it's not equal, it's wrong.
it's going to be 34. Yeah.
We
So
already
wrong.
know it's wrong because it's not the same thing.
Yeah. Now, if the real part of z is 0, then z bar is equal to negative z.
Um,
What do you think?
yes.
Yep. Z power 4 is equal to 4z. This is so wrong.
Yes.
So we are done.
So we have 1 is number 4.
Yeah. Okay.
So number 2.
Let S be the set of solutions of this linear system. So let's solve the linear system.
So we know that x1 equals x3 divided by 2. And we know that x2 equals minus x3x1 plus 2x4 minus 3x1 plus 2x4.
Okay.
So if we put, so we know that x1 equals x3 divided by 2. So so if we put x2 equals minus 3 times x3 divided by 2 plus 2x4, then let's say that x3 equals t, x4 equals s, then x1 equals t over 2, x2 equals minus 3 divided by 2 times t plus 2s, x3 equals t, and x4 equals s. So it is a half minus 3 a half 1 0 t plus 0 2 0 1 s.
Okay, what did you get?
Um,
Can you give me your final solution?
so I got a half minus 3 divided by 2. So I got t plus s. So a half t for x, a half t for x1, sorry, minus 3 divided by 2. I got a 1 and a 0 plus s.
You could just say
uh,
comma.
0, 2, 0, 1. 0, 2, 0, 1.
0.
2, 0, 1.
Wait, 0, 2. 0, 2. Yep,
0, 1.
0, 1. So if you multiply this by 2, you should get 1,
1 minus
negative
3,
3,
2,
2,
and
0.
0.
1 minus 3, 2, and 0.
But we need to find if it's linear independence or not. Because for the question 2, answer 2, there's 0, 2, 0, 1, and I have this.
Mhm.
The number 3, I have none of them. Number 4, I have none of them. The number 5, I only have the 1 minus 3, 2, 0. And the 2, 0, 4, 3, I don't have this.
Okay, so let's check
if-
for independence.
Yeah,
So alpha plus alpha 1 plus 0 alpha 2 equals 0. This means that alpha 1 has to be 0, right?
yes.
Negative 3 alpha 1 plus 2 alpha 2 equals 0. Alpha 2 equals 0. They are
Mhm.
independent.
So both of them are independent.
Yeah. So you had your S and you had your T. So my matrix tells me if S is x3, then this is a half. And then for x2, it's negative 3 over 2. For x3, it's 1 and then 0. And then for T, x1 equals 0, x4. This one is nothing, has nothing to do with x4. At least x2 has something to do with x4. And then x3 has nothing to do with x4. I'm getting the same, 0, 2,
Yeah.
0, 2, 0, 1. What
So-
if?
So if both of them are independent, then
So you
the
could
base,
use, can you use this and this to produce this? So maybe multiply this by 2.
so you guys 2, then minus 6.
And then you add to this. So this is 2 plus 0, 2.
So you must, so it's 2 and 3. 2 times t plus 3 times t s. So it's 2. Then
2,
it's minus 6 plus 6 equals
0,
0. 4
4,
plus 0, 4.
3. So this is
Then-
okay.
Yeah.
Yeah.
So it must be the answer 5.
Yeah, we just needed to show that this vector is inside the, a basis is not unique. And by
Yes.
not unique means that we have like so many bases. So the only thing we needed to show here was that this number
Mhm.
is inside the space that we came up with,
Yeah.
space of the two vectors. Find values of P such that the determinant of the following matrix is 0.
So find. So P must equal 1.
How
So
did you
it's
get that?
intuition.
Yeah, good intuition. Because
Yeah,
you only need
yes,
to have 2 rows or columns being dependent, right?
yes,
And then when you see the only thing making these 2 rows to be independent is P equals 1. So at least
yeah.
we have P equals 1. But what is the other one? It's 1 and something else. So it could be that, it could be this. So is the other one going to be -1 or is it going to be 0?
So we should try it using one of them.
Yeah, we can.
If you try using, for example, the 0, we get 3, 1, 0, minus 2, 0, 1, 0, minus 2, 2, minus 2, 0, 4, 3, 1, 2, 4. Then we just do the determinants. So it will equal us 1.
So you do the determinant and check if it's going to give you a 0.
Yes. It's gonna be a long one as it's a 4 by 4.
Yeah. I think I would first go 3, 1, 2, 4, 2 minus 2, 2p 4, 3p 1, 0 minus 2, 3, 1, 0 minus 2.
Mhm.
Then I could do 2p 0, 0, 3, 2, 3p 3, 1 minus 2, 1, 1, 2, no. And then 4, 4 minus 2, minus 2.
I'm sorry, what did you just do?
I moved this row to the front. It became this column. I moved it. So it's
Or can you do this?
yes, you're allowed to move columns, to move rows.
Oh, I didn't know about columns. I knew
Yeah.
about rows, but not columns.
Yes, you can move your columns as well.
Okay.
Yeah. A matrix
So
is just like equations. You can move an equation, you can move variables. For example, if you are doing an equation starting with the x's and the y's, you are allowed to switch, like to bring the x's, to bring the y's before the x.
mhm.
Okay. I was just trying to do this because I wanted to use the column with the greatest number of rows to find determinant. For example, that determinant is going to be 2. Determinant of 2 minus 2, 4, 3p1 minus 2, 3, 1 minus 2. And then minus 2p, 3, 1, 4, 3p minus 1 minus 2, 3, 1 minus 2. Okay. Wait, why did I write minus 1? It's 3p1 minus 2.
So I did using the zero, determinant using the zero, and using your echelon form you just did. So I got minus 16 using 0.
But okay, I'm not trying. I'm assuming the answers are not there.
Mm-hmm.
I'm trying to see if I can get the 0, or maybe if I can get, for example, when you look at this one, when you look at this first one, do we really need to compute this? This is going to become, the determinant is going to be 0 because -2, 1, 1, and 4, -2, -2 are dependent, right?
Yes.
So we don't even need to compute that.
Mm-hmm.
Do we? We don't. And then for this one, we could,
I know I got 0.
which one? For this one?
This one too, because they have 2 dependent ones also, so it becomes 0.
Which ones are dependent?
3p1 minus 2, 3, 1 minus 2, so the 2p.
But you see, I'm assuming p is not 1. They can only be dependent if p was 1. I'm assuming we don't know the value of p. At least we can see that if p is 1, they're going to be dependent, right?
Mm-hmm. So how do you know that the other one next to it, to the left, you know it's going to 0?
This one?
Yes, because there's 3p there.
No, I didn't use the row with the p. I used this column and this column.
Okay.
And I saw that is going to become a 0. And so I didn't even struggle to find that determinant.
Okay.
Yeah. So now I can do, yeah, this one is going to be a long one. Is there a shortcut? Yes, we can do a shortcut. We can reduce it. We can do, we can subtract this row.
Yes. So it becomes 0, 0, and minus 6.
Minus 2p. This is 0, 0, and 6, right?
Yes.
And this is 3p.
3p,
1 minus 2, 3, 1 minus 2. And so this is going to be minus 2p, 6, 3p, 1, 3, 1. So this is going to be minus 12p, 3p minus 12p
times 3p
times
minus 3.
3p minus 3 equals 0.
Yes.
divide by -12, you get P. 3P equals P minus 1 equals 0, right?
Did you divide everything by 3?
I divided everything by 12, by -12.
Okay, well, so how did you get 3p? It's not
So when I
really
divided that, I got 3p minus 3 equals 0. And I also had p.
Yes.
So I factored out 3. I got 3p. Then I had p minus 1 equals 0.
Okay.
And so if this is the same as p minus 1 equals 0, because we can divide by 3, right?
Yes.
And so p minus 1 equals 0. This only means that p is 1 or p is 0. There you go. And so that's our answer.
Okay. Number 4.
Yeah.
Okay.
You see, it was a 4x4 matrix, and we had to be tricky because we couldn't just look for the determinant without trying to cut corners. You see, I started by moving this row up, and then this. So I moved these 2 rows up. So the 3, 1, 2, 2 minus 1, I brought them up. And then I took this column, moved it to the front. It became this one. And so I could just do 2 and 2p. And then when I did my 2, I saw these are dependent. That became 0. And then I focused on this. Again, I had to be tricky so that I could get 006 and compute my determinant.
So is it possible, could you go back with the, yes. Is it possible to, so you know the determinant, you always choose the first row or the first column.
Yeah.
So can you choose the first, here is a 4x4 matrix, so you need to do the determination calculation like twice.
Yeah.
So could you do the column, then once you did the column, you do row? You understand what I mean?
You're asking whether you could mix them up.
For example, for the matrix you did with when you placed the column 2 to column 1, it becomes 2p00.
Yeah.
And we use the first column to do the determinants.
Yeah.
And then it became 2 determinant, 2 minus 2, 4, etc., etc. And can you do, once you got a determinant, can you use as the row, for example, 2 times 2 determinant of 1 minus 1 and 1 minus 1?
Yes.
Did you understand what I mean? To once use the column, then
you use the rows again.
Yes.
Yes. You can use any row, you can use any column.
Okay.
For example, if I wanted, I could even do without moving this column. I could have used it at its position. Yeah, could have done it.
Okay. Okay, I understand.
All right. So they want us to find the dimension of the null space.
So to find a null space, you need to do the kernel before, with the null.
Yeah. You just solve the matrix.
Yeah. So so we already know that's a 4 times 3 matrix.
Mhm.
So it won't be 4.
Yeah.
Right.
So it cannot be 4.
So so should we do the kernel?
Mhm.
Okay, so
And how do we do the kernel?
so 2x minus 1y plus 3z equals 0. Everything equals to 0.
Okay.
And then we try to search what is x, what is y, and what is z.
Yes.
And then we know the kernel.
Okay.
So we know that 2x minus y plus 3z equals 0. And 4x. But could we simplify to echelon form before
That's the best way to do it.
to make it a bit simpler?
Yeah.
So we could
do
take
1, negative half,
half.
3 half.
I was more thinking about as the first column is they're all like 2, 4, 6, 8
Mhm.
even numbers. We could
Yeah.
do row 2 minus 2 times row 1.
And this would give you 0,
So 0,
negative 4,
negative 4, yes. Then 0. And we could do the same for the row 3
It would
by
be 0,
multiplying by 3. 0, then minus 3 plus it's
0.
0 and 0 again.
Oh, that just went to 0.
Yes. And then we do
Interesting.
times 4. So 0,
0.
0, and 0.
Oh, okay.
So we know that
So the dimension of the kernel is going to be 2. It's a filling.
so we could calculate the rank and then do, for example, the number of columns minus the rank. So we know that it cannot be 3.
The rank is 2.
The rank is 2, so it's 2 minus 3.
Dimension of the matrix is 4.
3 minus 2 is
4 minus 2 gives us 2.
sorry, why is it 4? Is it not 3, the number of columns?
Oh. Okay.
I don't know, it's a question. Is it not 3? Because normally it's the number of columns minus.
We usually think of it of the number of columns. But you know, whenever we are talking about a matrix, for example, we usually, the real dimension would be 4 by 3.
Yes.
Okay, why don't we solve this and get, if we get 2 different solutions, then the dimension is going to be 2. If we get 1 different solution, yeah.
So we know that x minus a half y plus 3 half z equals 0, and y and minus 4y equals 0. Therefore, y equals 0. So we know that y equals 0, then x.
Okay, minus 4y equals 0. This means that y can be any number.
Oh, yeah, true, true.
It's free.
But is it not 0? Why is it not 0?
Y is not 0 because, no. Y is 0. I'm going crazy. Y has to be 0.
Yes. So y is 0. Therefore, x plus 3 divided by 2z equals 0. Then x equals negative 3 divided by 2z.
And so the basis is going to be 1, 0, negative 3/2. The dimension is going to be 1. So
Yes.
you are right. So the dimension was 3, the rank is 2, 3 minus 2, 1.
Should we verify to be sure that's the correct answer?
Yes, we did.
I
We-
should check the solution.
Oh, okay, okay.
Oh, it's 2. Yes, it's correct then.
Okay.
Sorry.
What?
But is it not? Because the dimension of nullity is the number of rows minus the number of the rank.
The dimension of the nullity?
Yes. Is it not?
I started by saying 2 because when I saw 2 0 rows, I was like, the dimension of the nullity is going to be 2.
Because I wrote down that the dimension of nullity is the number of columns minus the rank. And so it would be 3 minus 2, which would be 1. But how do you know that the rank is 2?
Because I have two linearly independent rows. Let me check the solution one sec.
Because the solution says rank A equals 1. And by rank nullity theorem, it follows that dimension null is 3 minus 1, which would be the number of columns minus the rank equals 2.
It says the rank of A is going to be 1.
Yes.
Oh, look, we reduced it badly. This is 4 minus 2, 0. And then 2 minus negative 2. 2 minus negative 2 is positive 4.
So 2 minus
6 minus 6, 0.
2 times minus 1, so it is 4.
So they're saying the rank is 1.
Yes.
The rank is not 1. The rank is 2. I don't know why they're saying that the rank is 1. I'm not able to open the solution. Just okay. When you look at that matrix, do you think the rank is 1?
I was thinking about 2 also.
Let me look at the solution.
The solution says it's 1.
The rank of A is 1 by rank nullity theorem. 3 minus 1 equals 2. Oh. The rank of A is 1.
It's very weird because I went in the internet and searched rank calculator, and I inserted the matrix, and it says that the rank is 2. Oh, there's a mistake. I saw the mistake. So in the solution, we have the matrix equals 2 minus 1, 3, 4 minus 2, 6, 6 minus 3, 9, 8 minus 4, and 12. But in the question, the minus of the second row of minus 2, of number 2 is not, we can't see it.
Yeah, there is a mistake. So there should be a minus there for the answer to work, right?
Yes.
Yeah. Okay. So let V be a vector space with dimension V equals n. If B1 up to Bn in V are linearly independent, then they form a basis of V. If V equals the span of that, then M, okay. Yeah, just give me 1 sec. I want to take an off. I don't want anybody to book me after. Wait, somebody already booked. No. No, I need to take some time off. Okay, let me think about it. So a student wants to book me by force. And I'm like, I'm so tired. Okay, so we go to 5, right?
Yes.
So let V be that vector space. The dimension of V is n. If B1 up to Bn are in V, if these are linearly independent, then they form a basis of V. That's true, right?
Yes.
If V equals the span of those basis elements, then M is less than N. That's not true, right?
Yes.
If B1 up to Bm in V are linearly independent, then M equals
Then
N.
M equals N.
That's true.
But that's not That's maybe it's true.
No, that has to be true.
Mm.
Okay, wait. No, could be true. You're right. Because they are not bases.
Yeah. Doesn't say there are bases.
Yeah. So every set of generators of V contains exactly n vectors. That's true. True or not?
Every set of generators of V contains exactly n vectors. No. Because it contains n vectors. It doesn't say contains n dimension vectors. Like because a vector is a vector is, for example, 3, 1, 0, -2, and if we want the dimension to equal the number of vectors, the number of vectors, like it doesn't make sense.
So the only time they would be n vectors is when they are independent. If he was talking about independent individual vectors in V that are generators, if they are independent, they would be n. But now here he's not specific. He's just picking a set of generators of V. So the fact that he's not specific is making us conclude that this is not true. And then the last one.
Because I was more thinking about
not true.
That the number of vectors doesn't tell you the dimension, because it could have hundreds vectors of 2 dimensions.
Yeah.
So the last one is B1 to Bm inside V are linear dependent, then M is bigger than N. No, should be wrong. Yes, it's wrong.
Yeah.
Because in a vector space with dimension V equals N. Wait, why is it wrong? Oh, it's linearly dependent. Oh, sorry. Okay, yeah, it's definitely wrong then. Why is it wrong?
I'm thinking about it. So B1 to Bm in V, they are linearly dependent. Then M is greater than N. Not necessarily. It's wrong. Let me show you an example. Take R3, right?
Yes.
N is 3, right?
Yes.
Take B1 to be 100, right? Take B2 to be 200. These are linearly dependent vectors, right? And they are in R3. And this means that M is 2, right? It's not greater than N. So the statement is open. M could be greater than N, but at the same time, it could be less than N.
So it's like, could be true.
Could be true,
so it's
but
wrong.
not always. So it's wrong.
Yes. Yeah. And for the, if B1 goes to Bm inside V are linear independent on the third one, then M equals N. Why is this?
It's because you could pick linearly independent vectors. For example, look at R3. Pick 1, 0, 0. Pick 0, 1, 0. These are two vectors, linearly independent. And how many are they? 2, right? But
Yes.
N is 3. So we have found a case where I picked linearly independent vectors and they were less than N. So could be, again, this is a could be true. So not always true.
Yes.
Yeah.
Okay. Number 6.
All right. So for which of the following matrices A is the linear map LA defined by LAV equal to AV surjective? So it's going to be surjective if
For which of the following matrices A?
but now they are not telling us where A is coming. Okay, we can know that. For example, in number 1, A is taking us from R3 to R2, right?
Yes.
So we need to show that the dimension of A, you just need to show that the dimension of the image of A is 2. Just need to show that the dimension of the image of A is 2.
So to know if it's surjective, because they're talking about a linear map.
Yeah.
So to be just surjective, what do you need to have? What are the properties?
To be surjective, you just need the range of the linear map. The range or the image of that linear map LA has to equal the codomain. It has to map, it has to make sure that everything in the codomain is matched with everything in the domain. Yeah. So you just need to show that because it's taking us from R3 to R2, right?
Yes.
You just need to show that the dimension of its image is equal to 2. Okay.
Okay.
Another theorem says that the dimension of the okay. I wanted to use a theorem that connects the kernel to the dimension of the image. Remember we talked about, I'm trying to remember what we said about the image. Yeah, we talked about this the other time. We said that the image of A is the column space of A, right?
Mhm.
We can create the image of A using any of the columns as our basis, using all the linearly independent columns as our basis, right?
Yeah.
And so this is going to be, the basis is just 2, 4. So we only have one basis for the column space of A. And so the dimension of the image A is 1, not 2. And so this is not surjective.
Okay.
Is that clear?
Yes.
Let's go to A.
So,
What is the dimension of the image of A for the second one? Just by looking at it,
2.
2. And so this is
Yeah.
going to be surjective.
And the other ones are wrong because they have the they have three rows.
So for the other ones, we need to check. Look at this one, the third one. It's taking us from R2, right?
Mhm.
And it's taking us to,
Is it not R3 to, no, sorry, R2 to R3?
it's taking us to R3, right? So you need to look at its column space and find out whether the dimension of its image is going to be 3. Actually, just by looking at it, its dimension is 1. The dimension of the image of this one is 1, right?
Yes, because it's the same as A, but just transposed.
Oh, and by the way, the dimension of your image, it's just your rank.
Yeah.
The dimension of the image is the rank. And this is going to be, rank is 1. Rank is not 3. Okay. The next one, the rank is 2. The rank is not 3, right? So it fails. And then for this one, it's taking us from R2 to R2. So is its rank 2? No, its rank is 1, so it fails. And so we go with the
Yeah.
first answer.
No, the second.
Oh, the second.
Yeah, the second. If we check the answer.
It's the second. I remember. You can see I ticked the second and then I forgot.
Yeah, it's the second.
You know, I ticked the second and then I put a mark on the
Yes.
first one. So I'm like, yeah, the marks
Yeah, it's the second.
confused me. Oh, this paper is easy and motivating.
Yeah, it feels easier.
Oh, let me see if we have a conic down here. If I see a conic, I'm going to run. Ah, no conic. Nice, nice. This is a nice paper. Okay. Find the value of the parameter k such that v is an eigenvector of A. Didn't we do this? They repeated it. You know, this is telling you that your exam, most probably they are going to repeat some of the questions.
Yes, that's good.
Yeah. So an eigen such that, find the parameter k such that v is an eigenvector of A.
So first we need to find eigenvalue.
Eigenvalues are 1 and k minus 1.
Um, is it one? Because it has so 1 minus lambda times k minus 1 minus lambda. Therefore,
You're looking for the eigenvectors
yeah, so lambda needs to equal 1 or k minus 1, yeah, okay.
you see, I just looked 1 and k minus 1 because this
It
is
has a
an
0.
yeah, it's an upper triangular matrix.
Oh, could you explain me quickly the upper triangle matrix?
It has zeros below the diagonal line.
Mhm.
There is nothing below the diagonal line. So if there is nothing in below the diagonal entries, then the entries in the diagonal become your eigenvalues. And so 1 and k minus 1 became our eigenvalues.
Okay.
Yeah. One and k minus 1.
K minus 1. So now we need to find the eigenvector. So the eigenvector must be
So let's find
so
an eigenvector associated with 1. This is going to be
1
0, 2, 0, k minus 2.
0, 2, 0, k minus 2. So it's going to be 2y equals 0 and k minus 2 equals 0. Therefore, y equals 0. Then k equals,
So that's not going to work, right?
yes.
So we find an eigenvalue associated with the other eigenvector. So we are going to do 1 minus k. 1 minus k minus 1 is 2 minus k. 2,
Yes. No,
0.
it's going to be 1 minus k minus 1 would be minus k.
Oh, 1 minus k minus 1. This is 1 minus k plus 1. 2 minus k.
Okay.
2 minus k is 0. And then 1, 2. So 2 minus k x plus 2
y.
y equals 0. This means that 2 minus k equals 2 minus k x equals
negative
2
2y.
negative 2y.
Yeah.
Now let y be 2. Let y be negative 1.
So it
Okay.
becomes 2. Therefore, 2 minus k x equals 2.
Wait. Wait. Let x be 1. So y is going to be equal to x divided by 2 minus k, right?
Um, um,
Wait, y?
no,
No, wait. Why am I so confused? X 2 minus k divided by 2. Now that's right.
yes.
And so if I'm creating my vector, if x is 1, then y is going to be -1, 2 minus k divided by 2, right?
2, yes.
Which is going to be k minus 2 divided by 2, right?
Yeah.
So if x is 1, then this is k minus 2 divided by 2. And this has to be 2, meaning that k minus 2 has to be 4, and so k has to be 6. So the answer is
Wait,
6.
how do you know that it must be 2?
Because this is the vector we
Oh,
want.
yes.
So it has to be.
So yes. Okay.
So it has to be 2.
Yeah. Okay.
Do you remember how to check a subspace? Oh, can you confirm whether question 7 is right?
Question 7. Yes, it's correct.
Okay. So which of the following subsets of R3 is a subspace? How do you check a subspace?
Hmm.
Do you remember the definition of a subspace?
No, I forgot.
Yeah.
Subspace.
Yeah, it's okay to forget. Okay. Is it okay if we start from here? So when are we meeting again?
Yes.
Oh,
So
you haven't scheduled.
no, I haven't.
Okay.
I need to. So I don't really know my timetable for the
Okay.
next day.
Yeah, you're going to schedule.
But I will schedule.
Yeah.
It's probably gonna be either Monday or Tuesday.
Okay. So this paper has lifted your moods, right?
Yeah.
Yeah. Number 8 is also so easy. We are going to use the definition of subspace.
Mhm.
And then number 9, consider the orthogonal complement. Yeah, we look at the orthogonal complement. Which of the following matrices is orthogonal? Okay, easy peasy. Consider the following. Given that parametric equation, L and pi are parallel. So this is about, what are we calling it? Projections.
Projections, yeah.
Yeah. Okay. Oh, this is a conic.
Yeah, I think so.
Okay. Yeah, by Monday we will be having a good understanding of conics. I have to, yeah, looking at conics using matrices is something that came up in my mind today. It's something I need to look into, because when we were studying conics, we never ever used their quadratic forms. We would just complete the squares nice and good, and they were easy conics. But this type of conic, the one your professor is giving, you cannot avoid using the metrics, the quadratic, the quadratic forms.
Yeah. So for next lesson, we should know about conics a bit more.
Yeah, next lesson I will take you through the conics. I will probably explain to you why we change those bases the way we do.
Yes.
But yeah, that's something I should do.
And I had a question. So do you in January or
Mhm.
after Christmas, which would be like, I don't know, maybe the 26, 7. Do you have any I don't know, holiday dates that you have that you want to teach?
I don't have holidays. I even don't, even on, I'll be teaching on Christmas actually.
Oh,
Yeah, if I want to rest, I don't do it on a holiday. I just do it when I'm tired.
okay.
For example, tomorrow I'll be traveling.
Yes.
So I won't work during the day. I will only work during the night, and I'll just be able to see 2 or 3 students, you know?
Okay.
So I just take my breaks depending on how I feel. Like right now, I'm so tired. The student who is coming next, he's coming like 2 hours from now. I have to tell
Yes.
him that I cannot manage to see him.
Okay, just to know so I can schedule
Yeah,
my times.
yeah. So you can just schedule your times any day, even on Christmas. If I'm tired, I'll tell you,
Okay.
but I will not be tired. I will try not to be tired. Yeah,
Okay.
yeah. And also I don't have so many students. So the only thing that can make me tired is driving for long distances.
Yes.
Yeah. For example, today I drove to the big city. There was a
Mm-hmm.
lot of traffic jam because they are building.
Yes.
Our country is developing. I know your country
Okay.
is nice and good. Everything is okay. So in our country, they are building a road that is
Yes.
crossing the city, and it's in the air. It's, I don't know.
Okay.
Do you have it
Like
in your
a
country?
bridge.
You do, right?
Like it's kind of a bridge.
Yeah, it's like a road that is crossing the city, and it's way above the city. It's way above the buildings. It's like cars traveling, um, cars moving on top of me, you know?
Oh, okay.
Yeah, so they were building that, and there was a lot of traffic. I stayed in traffic for like 4 hours. It was so tiring. Yeah,
Oh yeah, 4 hours must be long.
yeah, it was so long. So I don't think I'll have any such cases. If you want,
Mhm.
you can book tomorrow, but tomorrow I will not teach you quadratic forms. I will not have studied that. If you book tomorrow, we can finish that paper, the easy paper, the one we are doing.
Yes.
Yeah.
So no, but
Any time
tomorrow
you want to book.
tomorrow I don't think I can.
Oh, you already said Monday. Yeah, we'll see you on Monday. I
Yeah, yeah.
remember you said,
Monday or maybe Tuesday.
yeah,
I will it in advance.
okay.
So don't worry about it. But
All right.
yeah, it will be next week.
Okay. So we'll see you next week then.
Yes.
Yeah.
Then okay. So could you? So you scheduled also the recording when you're gonna send the
Yeah,
recording?
I just made a schedule for that because I think everything I do depends on the schedule. If I don't write it on my schedule and get a reminder, I really don't do it. But now
Mm-hmm.
because I've set to do it on my calendar, I'll do it
Yes.
on Saturday.
Okay,
Yeah,
that's good.
yeah.
Then see you next week.
All right. So see you next week. Remember to confirm the lessons as well, or maybe you have.
Yeah, I have
Let me check. Okay. So
both of
see
them.
you next week.
See you. Goodbye.
Bye bye.